Okay, so today we're going to talk about dynamic programming, and we're going to look at it through the lens of recursion and memoization, two techniques that we mentioned already, and we're going to do it through the lens of Fibonacci numbers because it's a cute, simple problem that is a fruitful ground to demonstrate various techniques. Okay. So Fibonacci numbers are a sequence of numbers that complies with this recurrence. So F0 is 0, F1 is 1, and then for the nth number we have this recursive formula. I'm sure that you had seen this sequence before. It's a very natural sequence: 0, 1, 2, 3, 5, 8, 13, 8 plus 8 is 21, 34, and so on. It goes on to infinity. And this sequence is quite interesting. First, because it has this recursive definition. And interestingly enough, you can in fact define a closed form formula for the n number in this sequence. This is known as Binet's formula, which in a supplemental, I'm going to prove it, by the way, if you're interested. It's very simple to prove. So it says that the nth number is essentially phi to the n minus 1 minus phi to the n divided by square root 5. The interesting thing is that phi here is the golden ratio, which is roughly 1.618. Of course, again, it goes on to infinity. And of course, if you look on the formula for the nth Fibonacci number, of course, or the number again, this is just an approximation. But if you look at it, this grows exponentially. This flips the sign, but goes down to 0, right? Because it's smaller than 1. So it really is that the nth Fibonacci number is really roughly like that. Right, this is a good approximation, especially as n becomes bigger, and that will be useful later on. Okay. So, of course, the natural question is how many bits do we need to write the number fn in binary? And if fn is equal to roughly 1.618 to the n divided by square root n, then, it goes exponentially, right? So you're going to need, well, I'm saying all the time, so it's a bad habit. So the number of bits you would need is definitely this number is definitely smaller than 2 to the n, and as such, the number of bits you will need is smaller than n bits. Right? If you think about it, this is going to be larger than probably something like n over 2 bits. So it's somewhere in this range between n over 2 bits and n bits. Right? Okay. So the correct answer is as such this. The second answer. Okay, so Fibonacci number grows quickly. This would come back to bite us later on. But for the time being, let's ignore this issue. And here is the recursive formula to compute Fibonacci number. If n is equal to 0, we return 0. If it's 1, we return 1, right? The base cases. And otherwise, we call recursive. Right? And we just add up the two numbers. Okay. Okay, now what's the running time of this recursive formula? Well, if you think about it a bit, it just follows the recurrence, right? You call recursively on that, so this is tn minus 1. You call recursively on that, this is 1. And then there is some, some additional work, it's constant amount of work, right? So we get this recurrence. And this recurrence is essentially very similar to Fibonacci. And in particular, one can prove that, in fact, T of n is bounded by the nth Fibonacci number. So T of n is bounded by this golden ratio to the n, which means that the running time is exponential. So, of course, the natural question is we can do better. But before looking at that, let's look on the recursion tree, right? So Fibonacci of 0 and 1 create a recursion tree of singletons. 2, we do 2 recursive cores. 3, if you compute recursive with 3, we do recursive call on 1 and 2. And, when we call on 2, we essentially, the recursive call that we are computing is identical to this recursion tree. And it continues in this fashion, right? Right, we get these trees. Those trees, by the way, are known sometimes as Fibonacci trees, and they're used in something called Fibonacci heap, if you're really interested. But, if you look on the bigger trees, right, what you would notice, right, this is for, let's see, for which value is this? For 7, right, you get this huge tree, but it has a huge amount of repetition, right? This subtree, 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 and this subtree are all the same, right? They're the value associated with Fibonacci number of 2, right? And the intuition is that since the calculation in this subtree, recursive subtree, is always the same, we don't need to do it more than once, right? Because once we do it once, we remember the value, and next time we try to perform it, we can just fetch the value. So this is the basic idea behind memoization. But before going into memoization, let me, of course, recall that there is the simple iterative algorithm, which just fills an array F, right? Where in the first entry and 0 entry, we just write the value 0, 1, right? And then we just fill the array from left to right, where at every point we just add up the numbers. We go from left to right. And of course, the running time of this algorithm, if you think about it, it's a simple loop. So that takes, it's a loop of n steps. Every step we are doing a simple addition operation, so it's O of n time. Right? So this is O of n. So this is a huge improvement from exponential time to linear. So that's kind of surprising. And by the way, I would mention that one can even do better, strangely enough, if you want to see the supplemental. So the natural question is, how do we get from the recursive algorithm to this algorithm, which is done through this memoization that I mentioned earlier. So, okay. Okay, so what's the difference between the recursive algorithm and the iterative algorithm? The difference is that the recursive algorithm recomputes again and again and again the same value, and the idea behind memoization is just that we remember the results of previous computation and we don't repeat them if we don't want to. So a dynamic programming can essentially be thought of as finding a recursive solution that if you use memoization, it becomes efficient. Usually, most recursive code for the problem we would look at if we implement naively take exponential time, or even worse. But once you use memoization, suddenly the running time becomes near linear or quadratic, much better. So it's kind of a pretty magical approach. Now, the classical approach to dynamic programming is even more low level. We will speak about how to get to this lower level representation where you just fill up a table later on. Okay, this is it for now.